Okay, cool. All right. Thanks so much for coming, folks. It's lovely to be here. So I've been billed as the space guy, and I'm like delaying you from drinks. So that's really an ideal slot. I'm going to tell you a little bit about our group at Curtin. What we are, what we do, and touch on some of the different technologies that we've used to get at kind of research goals in planetary science, and a whole bunch of those are missions. So a little bit about some of the missions that we've done and some of the ones that we're planning. The big thing that we're interested in is kind of origin and evolution of the solar system. So how did we go from, dust and gas to planets capable of supporting life? And that's always been the thing that's kind of, moved me in my career, and that still does. And now I'm just really pumped to be in a position where we can actually think about leading our own Australian missions to advance those sort of goals. So one of the project that I actually came to Australia to do is called the Desert Fireball Network. I've been here 10 years, and that's still running. The idea with this one is that when we started, we really had no idea where meteorites came from in the solar system. Now, meteorites are just these kind of beautiful samples of, hundreds of different solar system bodies that we get for free because they drop in, like all over the world. So it's kind of free sample return missions, but we have no idea where they come from. So what we thought was, okay, let's build, if we can build kind of remote observatories that operate autonomously and see the whole sky, and we can track the fireballs as they come in, then we can triangulate that information and track it back to get orbits for those objects. And if we can actually get the rock on the ground, then it's kind of like, okay, we know it came from this asteroid, and we know it came from the Kuiper belt. So we'll have a context for understanding the composition of those things. So that was kind of the first time in my career that I wasn't going into a lab and operating a microscope and actually just getting data like that. I was working with engineers to accomplish a goal together, and that was a lot of fun. So this is kind of an example of the sort of data that those stations got. And this was, so this started as a collaboration with the mechatronics team at Curtin, and that's grown into, we're now kind of all part of the same center together. This is the data set that we've got now in terms of orbits for all the fireballs that we've seen. We've actually got more data than has existed out in the literature in human history. So in terms of where small bodies are in the solar system and what the environment is that Earth kind of goes through as it orbits the sun, where those objects come from, where the things come from that hit us, the data set that we've got is now the most complete one that there's ever been, which is beautiful. Some of you can see there's kind of clusters there in some of those orbits. That's debris from comets, like larger chunks of stuff from comets that have similar orbits to that parent object. This is how we kind of work out where the thing lands. So we use a bunch of different analytical approaches to kind of model the entry of it through the atmosphere, and then when the light goes out, we can actually pinpoint it within 10 or 20 meters, even from like 150 kilometers distance when the fireball is visible. But when the light goes out, we have to kind of model where that thing goes from around about 20 kilometers up. So we sort of build a volume around it, and then quite complicated sort of atmospheric models like atmospheric pressure, winds, and okay, is it a brick or is it a sphere, and what is its density? And there's a whole bunch of variables there that we try and model so that when we go out in the middle of nowhere, we're not kind of trying to tramp around on a huge area. The first one that we found was actually in Lake Eyre South, which is, it's the biggest salt lake in the world. And it was right in the middle of it, so not an ideal location to get to, but we found it, and it was actually buried. It had kind of made a little splat in the lake, and we dug it out, and there it was, and that was gorgeous for me, because it was, you know, on the one hand, it was kind of proof of the pudding that all of this effort that we put in with all of these observatories and the kind of autonomous data reduction pipeline that we developed, all of that works. And it was just awesome as well to actually, you know, put my hand on that rock, like buried half a meter down in the sludge of Lake Eyre, and try and yank it out. I was so excited I kind of shredded the tendons in my hand, actually, because I was really pumped to do that. So that's the kind of size of the Fireball network that currently covers Australia. We expanded that into a global observatory, and that's with collaborators in NASA Ames. So NASA has this program called SURVEY, which stands for Solar System Exploration Research Virtual Institute. They have a whole bunch of clunky acronyms, and it basically is designed to kind of pull together everything that the US does in planetary science and solar system exploration with a sort of human angle as well. So it sort of, you know, has a kind of applied sense to it in terms of furthering human exploration. And that's me signing the agreement on behalf of Australia many years before I became an Australian citizen. So I still don't know if I, you know, broke some law, to do that. So this is the current, all the teams that are part of the Global Fireball Observatory, and what we've done is help all those countries, all those teams set up their own Fireball networks, and then we kind of integrate all of that data, so we just get this giant yummy data set, and we can see meteorites landing all over the world, which is really exciting. Now, what we found is that, so you've got all of these observatories clicking away all across Australia all the time. And every now and then they turn up stuff that kind of surprises you, that's sort of flying around in the sky that you know, maybe folks didn't really want you to see. And one of the things that we saw was this little thing. And the reason that we were kind of given a heads up on this was one of our friends, who's sort of an amateur photographer, astronomer, takes these beautiful time-lapse pictures of the Milky Way, and he took this time-lapse, and over the period of about 10 minutes, you see this, what kind of looks a little bit like a fireball transiting the Milky Way, which is just ridiculous because, you know, our atmosphere is 100 kilometers thick. And it's going to take, you know, the longest fireball is maybe 20 seconds. So when we triangulated it, that was at 7,000 kilometers altitude, so it wasn't local. And for 3 days, we had absolutely no idea what that was. So you had a kind of a lab full of pasty, grizzled planetary scientists who had observed a flying object that they couldn't identify. And throughout that time, it was like, you know, how many disaster movies start with that premise? And, you know, a week later, the Earth has been destroyed. But what we realized was, in the end, was that it was actually the booster from a Chinese one of their rockets that I think is building their GPS network. And what we've seen was the booster from that taking that thing up to geostationary orbit. And we're able to triangulate it back to the launch center where that came from. And at that time, a whole bunch of people in black suits got interested in our work. and we realized that that we can also use our technology to track satellites. So so initially this was kind of, you know, this was it wasn't really a project that kind of tickled me in terms of, you know, the stuff that gets me going as a researcher, because the thing that moves me is to, okay, there's a problem out there, the universe works in this way, and I'd like to work out is that, you know, I've got an idea about how things work and how do we test that. Here it was kind of, you know, we'd got a really nice technology. It didn't really come together for me as a cute problem to solve. But where we got to in the end was that, you know, we need to know where all these satellites are. There is no such thing really as space traffic control, like, you know, the equivalent of air traffic control. So what we wanted to do was actually develop a system that could deliver that. And that ended up being an exciting one for me. So we built a network of kind of higher resolution cameras. Again, these things can sit out in the desert for, like, you know, 2 years without you bothering to look at them. Except these are all kind of tiling the sky so that you're triangulating. You can triangulate observations of satellites as they cross overhead. And, you know, as a researcher, it's really interesting for me there's a conference in, so there's a conference on Maui every year, because, of course, that's where you go if you're in the US military and you want to talk about satellite tracking. And that's where all the US military folks go, and the researchers and the private sector folks, and talk about satellite tracking. And what's really interesting for me was that no one had ever triangulated the position of a satellite optically. And, you know, and I would be sitting there listening to all these talks, and, you know, people, these were like billion-dollar telescopes, facilities, and no one had actually, like, triangulated the position of a satellite. You know, we have binocular vision for a reason. So it turns out you can do it with about the same precision as a $10 million telescope using 2 Canon cameras. Right. So, you know, yes. So, so this is what we ended up with. We've got a kind of a trial network that's set up now in Australia. So every night, this is kind of what it's seeing. The line on the left there is what the US Space Track Network delivers. So it should be seeing where that track is of that satellite. And it's about 10 arc minutes off, which translates to kilometers at that altitude. And the one on the right is where our network puts it. Now, the one on the left, that's like probably around $30 billion worth of assets delivering that data set. So I'm quite chuffed with this solution that we put together. I'm quite proud of that. Yeah. Now, the stuff that I really love is what we've done with missions and our mission involvement. And this was like part of my career, which was kind of the most, I think, exciting moments in my career. So, so I'll tell you a little bit about that, and then some of the stuff that we're hoping to do in the near future. I was, so on this, the kind of, so there's a bunch of these. This is like all the different members of our team at Curtin who've been on different missions there. The Stardust one was kind of a special one for me. So that was a sample return mission to a comet called Wild 2, and collecting dust from that comet and then bringing it back to Earth. And this is when I was at Imperial in London, and I was really expecting, I was so excited to get the dust and so we could analyze it in the lab. And I just imagined that, you know, this would be some, you know, like NASA security guard turns up with a briefcase sort of padlocked to his, you know, his hand, and it was DHL, and it was just such a letdown. you know, it's still really nice to get comet samples, but yeah. So so we've got a couple of people in my group who have worked on missions on landers. So this is the Huygens lander on Titan, artist's impression of Huygens. And this is one of the most remarkable missions for me. This is like, so Cassini-Huygens was kind of a double mission to Saturn. The Cassini, the orbiter that did flybys of kind of all of Saturn's moons. All the incredible images that you've seen of Saturn come from Cassini. And it carried a separate lander to go into Titan's atmosphere and land on the surface. And that lander was actually capable of landing on a methane ocean and floating, or a methane surface and landing on the surface. And in the end, it landed on, like, we had no idea because Titan's atmosphere is so thick. And it landed on the surface and sent back like the first incredible images of Titan. My first mission was this one, Beagle 2, which was a UK Mars lander that initially we thought it had been the UK's first crater on Mars, but it turns out it didn't actually splat. It was, we got an image like from an orbiter, from another orbiter much later, to show that only 2 of the 3 petals opened and it didn't have enough power to communicate. But it was just a really nice idea, and that was like, you know, that was me as kind of a young postdoc on that one, which was a really interesting start. The one that I'm on now, one of the ones I'm on now is OSIRIS-REx, and this is the launch of OSIRIS-REx from viewing it from the causeway at Cape Kennedy, and that was just, that was the first launch that I've ever seen, and it's exactly as incredible as you imagine it's going to be, and you can feel it in your chest, just like, you know, that was amazing. My kids were there and were not nearly as impressed as they really should have been to have been so lucky to have seen that. And yes, so, but it's an amazing mission, and OSIRIS-REx is an asteroid sample return mission. One of the really interesting things is kind of how we actually got the samples from the surface of the asteroid. So when we got there, the asteroid was actually a lot more boulders than we were expecting. So, so it meant that the positioning system that was designed for the spacecraft couldn't really give us good enough resolution to be confident that we can actually fit between those boulders and extend the arm down to grab a sample. So the team developed kind of a natural object identification system to compensate for that on the fly. So the actual positioning system for OREX was developed after the thing flew while we were at the asteroid, and because of that, you know, what we were seeing, and this was so cool to kind of be looped into mission control. What we were seeing was the spacecraft is saying, like, okay, I know where I am to plus or minus 40 centimeters or 50 centimeters, and anything less than a meter we know is going to be safe. And so, and then it's only there for, like, it touched down and grabbed the stuff, and then it was off again in like 2 seconds. And we got a whole bunch of stuff. So it's going to be fantastic. That'll come back in 2023, and we'll have those samples at Curtin to analyze. So that was us on kind of mission science teams led by other nations, and that's obviously fantastic and super exciting. What I wanted to do was start a program and see what we could do here in Australia and here in Western Australia to develop our own missions. Now, universities, you know, there's a whole bunch of universities that have developed CubeSats. CubeSats is really nice technology for unis to play with. You can build stuff fairly cheap. There's a whole bunch of stuff online you can kind of, you know, you can kind of buy. It's not quite like getting subsystems on Amazon, but it's almost. And now what was interesting was when we started this, we started actually as an honors project for some of our engineers. Well, when we looked at some of those subsystems, which were not cheap, it's like, you know, 30K for a power system, they really sucked. So, so we kind of made a decision right at the beginning to not do any of that, to kind of start from scratch and build our own, you know, spacecraft from scratch. And I'm so chuffed that we did that, because what it means is that, oh, wait a minute. There's a reason why I'm doing this, is that we can kind of churn them out. And this is one of our little spacecraft. This is kind of would be a ground model for the one that's currently in orbit if, you know, if we didn't kind of handle it like this. But what it means is that, you know, so if you've bought all that stuff online, if you're a uni that is doing that, and then you know, typically kind of lacing it together in a bit of a rat's nest, it's still really precious. That's probably cost you 200K to do that. So you can't test it to the extent that it really needs to be tested to be sure that that's going to be, you know, do a decent job in orbit. When we can churn them out ourselves, we can just test them to death, and we can go through iteration after iteration, and that's just been awesome. So basically, that's like everything on all of those subsystems on a single circuit board. And then, you know, what you've done then is dumped a whole bunch of the labor onto the circuit board manufacturer. And that's obviously a much better way of doing it. I like the little animations. So from my point of view, what that means is that, like I say, is that, you know, rather than kind of having every single spacecraft be a sort of a bespoke solution, requiring, you know, a great deal of labor. It's not like we get rid of everything. You still have to, you know, there's still the frame of it and the panels, and there's a lot of effort still that goes in that, and you've got to do that in a clean room. But we've dumped a lot of that effort onto the circuit board manufacturer, so we can leverage some of that consumer electronics manufacturing. The exciting thing for me then is that, you know, it means we can actually make these things really cheaply, which is kind of why I can just play around with one and bring it to a conference. And that means that we can help WA universities or SMEs or startups fly payloads for very low cost. We've got a program with high schools where we're helping high school students fly their own experiments in orbit, and that'll be starting from next year. So even like a 1U like that has actually got a decent amount of payload space left, and high schools will be able to build experiments to do that. And then it's, you know, it's also exciting for me because we've got we'll have on a path to get a planetary class spacecraft. So this is the first one. This was Binar 1, me being very proud, and I got the engineers gave me the honor of tightening the last little bolt on it, which was fantastic, and then they had to pull it apart again, and they didn't tell me about that. And this is just completely gratuitous. This was done by our, because I get a slomo, right, with the premiere, okay? I actually get a slomo. Now, I'm actually a really big Armageddon fan, and the slow-mo of all the astronauts, you know, as they come in. So that was really great. And what was lovely about this day was that you can kind of tell sometimes when it's physical like that, they're not sure what they're going to see, and there can be a bit of jokiness. And what was lovely was throughout that day, throughout that event, the premier and the deputy premier just got more and more excited and more enthusiastic, and it was just, that was lovely to kind of see that, you know, excitement and WA pride, and that's a really good photo, yeah. So So he was really excited, and that was really lovely. So that was kind of the, that was a really nice event before the launch. And then this was the launch. And I'd got it in my head that, that the deployment from, so basically the thing launches to the space station on a SpaceX rocket that's a Japanese resupply mission to the Japanese module on the space station. And I'd got it in my head that it was going to be the deployment from the space station that was the big deal. But it was just, so the state let us stream it from Yeagan Square, which was lovely. And I was completely unprepared for how pumped I would be to be seeing that with friends and family and colleagues, and it was just a wonderful moment. So yeah, I was kind of a bit, taken aback by that. Yeah, and that's my boy to the left there, looking just much less interested. Yeah, and I can tell you here that when we didn't hear from it straight away, my daughter said, "Epic fail, lol," right? Which I thought was a bit harsh. This is like 5 years' effort. But it was a lovely day, and that's the team. Now so that was the launch, and then 5 weeks on the space station, and then what JAXA did. So it's the Japanese Space Agency. They did this lovely thing, so they looped us into their control room, so that we could see it being deployed, and that was just really lovely. Now, so that was us at the deployment, and they took these beautiful images. So this is it. These are there was 3 deployed at the same time, so we're one of those. And just really lovely resolution pictures of the spacecraft coming out. I love those ones. And the Japanese astronaut, that was just so nice. So that's his, that's what he said. I hope it brings hope and joy, which was so lovely. So then it was in orbit, and then we didn't hear from it. Epic fail, Dad. And for 2 weeks we didn't hear from it. Now that's not completely unknown in. When you fly something, it can often take a while for the thing to, it'll try and boot up, and then, it's like all the antennae aren't deployed, and then you'll try getting through it in a different way. And I was fully in kind of morale damage limitation mode for the team. Good try, folks. Space is hard. Program, not a project. And then it got in touch with us, and it was actually kind of psychologically a little bit difficult to switch from, morale booster to. So that was lovely. So basically, the state that it's in is that we can't do everything that we wanted to do, but the avionics are all fine, and all the software on it is fine. So the main thing with this mission was a tech demonstrator to know that the new thing that we've built, doing it that way does work, and I'm really chuffed about that. Now, outreach has always been a big thing for us. So we had this display at WA Museum, which was lovely, called Big Binar, and it meant, so that the idea was that members of the public can post a message to space, which was really nice. And as I say, we're working with high schools and Indigenous students as well, Indigenous communities as well, to put in experiments on the next ones that we fly. So the next 3 are going to have deployable panels, so they're going to look really, really cute, like little birds, which is going to be beautiful. But you can probably tell that I'm not the most technically sophisticated project manager in the room. I'm a geologist, so there's really a very, very, limited range of, anyway. But that'll be lovely. And really, the whole thing here is a timeline towards where we do want to go, which is going to be the moon. And I'll just finish up by telling you a little bit about this. So this is part of our mission here, our project here, is going to fit with NASA's Artemis program. For those of you who don't know, Artemis is the NASA's program to return to the moon. It's like there's going to be, so next year, just from the US, there's going to be 3 private sector landers. The year after, even more, and an Artemis main mission element by NASA. It's like the next decade is going to look completely different than really anything any of us have experienced. Unless you live through Apollo, it's going to be bonkers. So for me, as a full-on space geek, it's just going to be incredible to see this. Oh, wait a minute. Now, the key element with Artemis that makes it different from Apollo is in situ resource utilization. And the idea here is kind of what NASA used to call live off the land. So if we can get ice on the moon, if we can find ice, then we can crack that for hydrogen and oxygen, and that's rocket fuel. And that means you'll be able to refuel rockets on the moon, and the moon has, piffling gravity well, and Earth has a really big one. So if you can fuel your rockets on the moon, you can go anywhere you want in the solar system, and it's super easy. And that's great. Now, the problem is that the ice that's been discovered is in this place, and this is Shackleton Crater, and the South Pole is just on the rim of Shackleton Crater, and it is exactly as forbidding as it looks in that picture. So Shackleton has actually the lowest measured temperature in the solar system. There'll be other lower temperatures, it's just they've not been measured. So it's 30 Kelvin in the bottom of that, with slopes of 30 degrees. So the idea is that we'll be harvesting ice at 30 Kelvin in absolute darkness down a 30-degree slope. Even as a geologist, I know that that's an engineering challenge. So our idea, is to send a mission that can do that can find alternatives to the ice at the poles, and accessible resources that we can get that don't have, you don't need to completely. You don't need to have like portable nuclear reactors, for instance, on the backs of rovers. So this is called Binar Prospector. Binar is Noongar for fireball in Noongar, and so that's kind of our heritage from the fireball network. And it'll be 2 small 6U spacecraft, so about this big. The main thing that they're going to be doing is so that's kind of a little render flying over the central peak of Tycho crater. And the main thing they'll be doing is magnetometry. Now, magnetometry is kind of the baseline data set that you want to do when you're finding resources. So this is the bit of geology that I understand. And the current data set really sucks. So it's 60 to 100 kilometers resolution, which would mean that you would not find any resources on Earth if this was the best map that you had. So we get better resolution by having 2 spacecraft traveling together. You can kind of, okay, have I seen an anomaly? I'm not sure. If your other spacecraft sees it as well, then yeah. And then by flying at really low altitude. And that's what's going to be so fun about this, because we'll be flying at really stupidly low altitude. I don't say it like that when I'm talking to my engineering team. And the other thing we'll be doing is thermal imaging, and that'll be trying to detect sort of local little ice traps that aren't, you don't have to drive down that horrible slope. So this is a render of what that spacecraft might look like, with the propulsion system there kind of on the right and the imaging system there on the left. And this was the plot that I loved, because as a scientist, the thing that I wasn't sure about was, okay, is that stable? I mean, can we can we have a stable orbit there? Do we have enough fuel to maintain it? Now, what that's showing is that, so we're building up a kind of a map there of the moon in the top right in those orbits. On the top left, they're bouncing around at about 19 kilometers altitude, coming down to about 9.4 and going up to 28. So 9.4 kilometers, so basically and then bottom left, those steps, each one of those is a burn. So that's the spacecraft, that's us telling the spacecraft, okay, you're getting too low, you've got to circularize your orbit, bump up again, and then you run out of fuel and you crash. But the idea is that, if we're there for 3 months, then we'll get a complete map of the moon at really, really nice resolution. And that is going to be so exciting because, so there on the right, that's on the far side of the moon, and there's actually a fairly small region that has altitudes above 9 kilometers. So it means that, and this is what I genuinely am trying to get the engineering team to swallow, that 9.5 kilometers is fine because there's only really a small part of the moon where we'll be flying underneath the peaks. So the goal is like really a kind of a unique high-resolution geophysical data set for the moon, and a big deal for me is just to capture imagery, kind of the like of which really no spacecraft has ever seen before. You'll be able to see, really like, okay, we're heading up to these mountains, and we're just going to clear them by a couple of kilometers. That'll be just beautiful. So these are the artist impression flying over Hadley Rill and the Apennines. That's near the Apollo 15 landing site. And a couple of things that, I'm really excited to see, okay, if we build that, then that's interplanetary class spacecraft platform that Australian universities can use for any other mission, right? So we'll be able to partner with other Aussie universities. They have an idea for a mission, they want to run it, we can help them with that. And we've built it once, it'll be, that's a lot easier to do it again. And then also this idea of kind of very low altitude observations, it's actually kind of in between normal orbiters and landers. So it's a platform that NASA's quite interested in as well. And that's another kind of cute animation of, they won't be quite that close together, but us flying over the rim of Tycho crater, yeah, and I think that's not bad timing. Okay, thank you very much.